Okay, so in this video, we will consider the topic of geometric vectors. Now you must have encountered vectors before in high school or even in your mechanics course when you looked at linear motion in 2 dimensions or 3 dimensions. So I'll try and go over this fairly quickly and then we can look at actual problems. We'll start with studying vectors purely geometrically first, and then we'll see that we can't get too far with geometry alone. And later on, then we'll add algebra into the mix and we'll realize that things are a lot more interesting when we combine the geometry with the algebra. But first, let's look at vectors geometrically. So what is a vector? Well, a vector is a line segment with a direction that is completely determined by the length of the segment and the direction. So consider drawing a line segment in the plane, and you have to give this line segment a direction. And of course, we'll draw everything in the 2-dimensional plane, but keep in mind a vector can be lying in 3-dimensional space as well. Suppose the vector points this way. So this is called a vector. Now this point right here is called the initial point of the vector. And this point right here is called the terminal point of the vector. And we usually denote vectors with lowercase letters with arrows on top. So you may call this vector, say, v, and put the little arrow on top to signify that v is a line segment, but not just a line segment, it is a directed line segment. And that is what the vector is. Now, the key definition is the fact that a vector is determined only by its length and its direction. So they are translation invariant. So you can move vectors in space, and as long as you preserve the direction of the vector and its length, the vector stays the same. And of course that brings us to the concept of equality. Two vectors are equal if they have the same length and the same direction. So if I translate this vector, say, here, and I try and draw the same direction and the same length, and I call this vector u, if the two vectors as line segments have the same length and have the same direction, then u will be equal to v. So vectors are equal if they have the same length and the same direction. Now usually the length of a vector, we denote it in the following way. So if you want to say the length of v, you would write double bar v double bar, and this is called the length of v, also called sometimes the norm of v. The norm is a synonym of length. So the norm of the vector v, which is simply the length of the vector. Now, there is one special vector called the zero vector. And if you think of it, the zero vector is the vector with zero length. So it has no direction, it's just a point. So the length of the zero vector is simply equal to 0. A natural question then is, well, once we have these geometric objects, can we perform operations on them? Can we multiply them by real numbers? Can we add them together and so forth? And the answer is yes. And we'll do everything in here geometrically. So the first question is, well, what if we multiply a vector by a real number? Let's start with just -1. So what if we look at, say, this vector? I'll draw a horizontal line, and say this is vector v. Then the negative of v will be the vector of equal length but opposite direction. And this is vector negative v. So that's our first definition. So given a vector, its negative is the vector of same length but opposite direction. What if we now try and multiply a vector by a real number? So suppose this is vector v. We may ask, well, can we make sense of, say, 2 times v? Well, naturally, you can think of 2 times v as being the vector of same direction, but twice as long. This would be the vector 2v. You could think, well, what if we do a third of v? It will be a vector of equal direction, same direction, but a third times the length of v. And that would be a third v. And you may ask, well, what if we multiply v by a negative number? What if we multiplied v by, say, -2? Well, it will be twice as long as v, with not the same direction, but with the opposite direction. So the length would be twice the length of v, but with a negative, it will become in the opposite direction, and that would be the vector negative 2v. And this is how you multiply a vector by a real number. If the number is positive, the vector has the same direction, and the length is multiplied by the real number. If the real number is negative, the vector has opposite direction, and the length of the vector will be an absolute value, the number times the length of the initial vector. So this brings us to the first property of the norm. If you ask what is the norm of k times vector v, it is the absolute value of k times the norm of the initial vector v. And this is called scalar multiplication, what we have here. So scalar is just a fancy word for a constant real number, and multiplication, of course, multiplication, so we can multiply vectors by any real number. And we have the property here, the first property of the norm. So this is how you multiply vectors by real numbers. The next question is, well, can we add vectors together? And can we subtract vectors together? Well, we already know that subtracting a vector is adding the negative, but how do we add vectors together? Right? This is our next question. How do we geometrically make sense of the sum of two vectors? Well, suppose we have the following two vectors. Suppose I give you, say, vector u, and suppose vector v is like this. So we have two vectors, and the question is, can we make sense of the vector u plus v? Now the key, if you think of these vectors as either force vectors or as giving you the position of an object in space or the displacement, it will actually make sense how to add the two vectors. So the idea is, if you do u plus v, let me translate the vectors in here. So I'll translate u, so try and keep the same direction, the same length. This is u. And to construct u plus v, you have to move v's initial point onto u's terminal point. And this is vector v. And I'll think of it as adding up two forces. So this is the force vector for u plus the force vector for v. So in the end, you went from here to here. So you have to connect the initial point of u with the terminal point of v. And if you do so, you form the vector that we will call u plus v. This is how you add vectors. You can also think of it as walking along a line segment from the initial point to the terminal point of the vector. So when you do u plus v, well, think of it as I'm walking along u, starting from the initial point, and I end up at the final terminal point of u, then you walk along u, and you end up here. So you started from this point, and you've ended at this point, so the vector is this vector, and that's u plus v. And this is how you add two vectors together. What if we subtracted two vectors? What if we said u minus v? Well, if we say u minus v, quite simply, we will think of this as doing u plus negative of v. So we can draw this a similar picture. So translate u again. As long as you keep the length and the direction the same, the vectors are the same. This is u. And we are going to add to u the negative of v. that is the vector of equal length, but opposite direction. So this would be negative v. And so we'll have now u plus negative v, or simply u minus v. We start from the initial point of u, we get here, then we subtract v, we get here. So we begin here and we end here. So this is the vector u minus v. And this is how you add two vectors together geometrically, and how you subtract two vectors together by adding, quite simply, the negative of the vector v. So now we have it. We have a way to add vectors together, subtract vectors from each other, and we have scalar multiplication, how we can multiply a vector by any real number. A natural question is, every time you have a structure, whether the objects are real numbers, functions, matrices, or vectors, you want to know what are the algebraic properties of the operations. And what's really nice about this is vector algebra behaves just like algebra on real numbers. Let's list a few of the properties, and then we'll prove one or two just to get a feeling for how you would prove the others. So let's look at, let's say, vector addition first. Vector addition behaves like regular addition of real numbers. It actually commutes, so u plus v will be equal to v plus u. Addition is associative, so u plus v plus w will be the same as u plus v plus w. And of course, all of these are true with subtractions and not addition. It all works the same. So addition, it commutes, addition is associative. We can ask, what if we do k times u plus v? Can we distribute the scalar multiplication? And the answer is yes. This is ku plus kv for any k. You can ask, what if we do a sum of two scalars? So a plus b, which are real numbers, times a vector u. Well, that would be the same as doing au plus bu, and so forth. So you can think of all basic operations you can perform with addition of vectors and scalar multiplication, and everything will actually be true. One last example would be a times bu. You could combine the scalars together as simply ab times u. Let's just prove one together, and you can look at proving the others on your own. Let's prove that addition commutes. And again, we're looking here at geometric vectors, so we have to find a geometric way of constructing this equality. Well, let's start with two vectors, u and v. And I'll already position them in the right way. So this is u. And if I want to add u with v, I will put v's initial point onto u's terminal point, and suppose that this is vector v. And so u plus v, think of it again as walking from the initial point of u to its terminal point, then from v's initial point to its terminal point. So you've walked from this point to this point, therefore the net result is this vector. So this vector is u plus v. Well, let's now do v plus u. I'll translate v so that its initial point is now in the initial point of u. So as long as I keep the length of v the same and its direction the same, these two vectors are equal, right? It's just a translation. This is still vector v. And I want to do v plus u, so I have to translate u's initial point onto v's terminal point. But if I do, look at the construction. Both of these are parallel of equal length. If I translate u up to here, this is now u. Well, both of these sides are also parallel and of equal length. So if I do v plus u, I've walked from here to here, and you see that v plus u is the vector lying on the diagonal of what we have, which is a parallelogram, because each pair of opposite sides are vectors that are equal, so they have same length and same direction, hence the opposite sides are of equal length and are parallel. So what we have with u, v, v is a parallelogram. And you can see that u plus v is the vector lying on the diagonal, pointing in this direction, and the vector v plus u is also on the diagonal, pointing in the same direction. But the diagonal of a parallelogram is unique, so clearly u plus v and v plus u are vectors of equal length and equal direction, hence they're equal. And this is how you prove geometrically that vectors on their addition do commute. And this is what we have. We have scalar multiplication of vectors, we have vector addition, we have the negative, we have properties of the norm. And as far as the theory goes, this is almost it. We're missing one little piece, and in our next video we'll consider examples, either little theorems that we can prove with vectors or simply monkeying around with vectors in given examples. Let's consider now the idea of building vectors from 2 points, because to build a vector, if you think of it, all you need is an initial point and a terminal point. And this will be our last idea, which is, as you'll see, very simple. If I give you, say, the point A in space, and again, the point A could be a point in the 2-dimensional xy plane or a point in the 3-dimensional space. Same goes with B. Suppose this is now point B. I can connect the 2 points to form a line segment AB, and if I choose a direction to that line segment, it becomes a vector. So imagine yourself standing at point A and walking to the point B in this direction from A to B, and this vector we call vector AB. So we write A because A is our initial point, B is the terminal point, and of course, to say that what we have is a vector, we include or write above AB a little arrow. So this means the vector AB, therefore, whose initial point is point A, whose terminal point is point B. Let's look at now some properties of this notation. They're very basic, but really useful, as you will see in our next examples. What would happen if we would do BA? Well, imagine the same picture. Suppose that point A is here. I'll try and keep them parallel. So this is still A and B. Just imagine them being in the same position. And now if I connect A and B, but I negate them, right? This is another vector of the same length and direction as AB, but in the opposite direction. So by definition, this is the vector negative AB. But we can give it a different name without the negative, because if you think of it, the vector negative AB is the vector that has as its initial point B and as its terminal point A. So it's just a vector BA. So you see, if you flip the order of the initial and terminal points, BA is negative AB, and vice versa, right? You could say that AB is the negative of BA. It's a dual property. So that's the first property. If you flip the order of the initial with the terminal point, so AB becomes BA, you're walking in the opposite direction. Therefore, the vector you get is the negative of the original vector. And one last property, which is the following. What if we have 3 points in space? And this is what we can call concatenation. So what if I gave you point A, say this is point B, and say this is point C? I can form naturally 2 vectors, vector AB. So we'll call this vector AB. This is now vector starting from B to C, or at least trying to get to C. So this is a vector BC. And now we can ask, what if we add AB plus BC? can we somehow simplify the expression? Well, so AB is this vector plus BC is this vector. So we started from here and we ended up here. So we get this vector. But if you think of it, well, we have the vector here whose initial point is A and whose terminal point is C. So this vector is just the vector AC. And so AB plus BC is just the vector AC. So we can concatenate the first vector's terminal point with the second vector's initial point. And think of it again very geometrically. Even if you forget this picture, think of it as you're at point A and you walk to point B. Then from point B you walk to point C. So the net result is you've walked from point A to point C. And therefore you get the vector AC. And with these few ideas, we will see that we can actually prove some some interesting results that you must have seen before, but maybe you haven't proved. And we'll look at some of these results, and we'll prove them geometrically using geometric vectors.